Good morning, students. Myself Pawan Kumar. So I will be taking inorganic chemistry from paper 6.2. Today we shall see about the first topic, organometallic chemistry. So first of all, we should know what are organometallic compounds. Organometallic compounds are those compounds which contain at least one carbon metal bond. That means it should contain one carbon and a metal. So metal can be as given, it can be any magnesium, lithium, lead, zinc, sodium, etc. Organometallic compounds are named by simply adding the name of metal to that of organic group bonded to the metal. So as you can see, some of the examples of organometallic compounds: CH3MgI, methyl magnesium iodide; CH3CH2MgBr, ethyl magnesium bromide; CH3Li, methyl lithium; CH3CH24Pb, that is tetraethyl lead. So these are some of examples, very common examples of organometallic compounds. So other way how you can define an organometallic compound is, an organometallic compound is broadly defined as one that involves one or more carbon atoms of organic group or molecule and a metal, that is metal can be a transition metal, lanthanide, actinide or main group metal atom. So here carbon and metal means carbon is an any organic group. So next, the compounds in which a metal atom, including non-metal and metalloid, that is which are less electronegative than carbon, is bonded directly to a carbon atom of at least one organic group, radical or molecule, are all known as organometallic compounds. The third way, organic metallic compounds are those in which central metal atom are bonded directly to the carbon atoms of hydrocarbon radicals or molecules. The term metal generally stands for elements less electronegative than carbon, such as boron, arsenic, silicon, etc. So any of definition also holds good. So one thing we should keep is, here carbon metal bond means a carbon is an any organic group and metal is generally a metal which is less electronegative than, it should be less electronegative than carbon. So naming of organometallic compounds. So in fourth semester you have seen the coordination compounds. So where naming of coordination compounds, we have some rules for naming of the coordination compounds. Now we have to name central metal atom or ion, and the ligands when there are two or more ligands. Some additional rules are followed in naming organometallic compounds along with the rules of the used for naming coordination compounds. Some of them here we can see is, the first point, ligands without prefixes mono, di, tri, etc. are named in alphabetical order irrespective of charge on them. So ligands are named in alphabetical order. So this is also one of the point used in coordination compounds. The presence of hydrocarbon ligands in coordination sphere is customarily indicated by name of their radicals such as methyl, ethyl, phenyl, etc. Although these are known to behave as anions in several cases. So thus according to this rule, you can name one of the example. K within the coordination sphere is boron, C6H54 is named as potassium tetraphenyl borate 3 complex. So another one, K within the coordination sphere, SbCl5C6H5 is named as potassium pentachlorophenyl antimonate 5 complex, so and so on. So in case of unsaturated molecule or groups, that is those containing more than one generally conjugated double bond, the ligand is named with the prefix eta-n. So this is one of the additional rule applied to the organometallic compounds, where eta n is number of carbon atoms in the organic ligand attached to the metal. When some ligand atoms involved in double bond or some ligand atoms in a chain or ring are bound to central atom, numerals indicating these ligands are inserted preceding eta n. So one of the examples how we can see here. So here is one of the compound. Here it is named as a bis tricarbonyl eta 5 cyclopentadienyl dimolybdenum. So the 5 indicates it is the ring, that is 5 cyclopentadienyl ring. So here in next example also you can see tricarbonyl 1,3 eta 3, that is it indicates number of carbon atoms. Eta 3 2-butyl cobalt. Third example you can see. So there are 4 carbon atoms, tricarbonyl 1 to 4 eta 4 cyclooctatetraene iron. So this is our name, an organometallic compound using. So when these are, that is unsaturated molecules or groups. EAN rule. So EN rule here means a 16 and 18 electron rule. So 18, as we know, so it is atomic number of an organ, so it is a noble gas. So whenever any compound that has 18 electrons by sharing or transfer of electrons, whenever that compound atom or element is having 18 electrons, then it has stable in nature, that is it has which is equal to the noble gas. So then we can say that atomic ion or whatever the molecular compound has attained stability. So now we shall see what is an 18 electron rule. A complex in which the central metal atom appears to have acquired the configuration of inert gas by transference or by sharing of electrons tends to be more stable. This generalization we call as inert gas rule or 18 electron rule. So total number of electrons which the metal atom appears to have around itself in the complex is called effective atomic number of the metal in that complex. So in coordination compounds we use to write EN rule with respect to the atomic number 36. So here we are referring to the 18 electron rule. So right. So the 18 electron rule implies that in a metal complex 18 electrons are made available to the metal through bonding, and then metal assumes electron structure of the next noble gas. That means the electrons which are accommodated, 18 electrons that are which are accommodated in the metal complex are 5 n minus 1 d orbitals, that is from each orbital can donate, or each orbital can accommodate maximum of 2 electrons, that gives a 10 electrons. From 3 np orbitals we get 6 electrons, and from 1 ns orbital we get 2 electrons, thus total making to be 18 electrons. 5 from d, that is 10 electrons from d orbital, 6 electrons from p orbital, and 2 electrons from s orbital, total making of 18 electrons. So which gives an which is an electronic configuration of an inert gas organ, which gives the stability to the molecule. So these electrons, so it not only belongs to the metal or element, these electrons comprise the electrons of metal together with the electrons contributed by ligands. The attainment of 18 electron complex leads to the stability of the complex. So how to count these number of electrons in a complex, that is an organometallic compound? The effective number of electrons, it is En, can be calculated by following some of the procedures here. So as we know, the 18 electrons comes from both metal as well as ligand, and some of the other ligands attached to the metal atom. So first point we shall see the count the number of electrons in the valency shell of free metal atom. That is, valency shell includes n-1 d orbitals as well. So this should be in your mind. Valence shell is not only n d, it is penultimate shell as n-1 d orbitals. Add or subtract electrons according as charge on the metal in complex is positive or negative. So you have to add electrons if that is a positive charge, or subtract depending upon what is the type of charge present. That is, if it is an ion, not in if it is an atomic state, then you can say it is 0. If it is ionic state, then you have to find whether you have to add or subtract. So second point, check the number of electrons which the organic ligands formally contribute to the valence shell of atom in accordance with the classification of ligands. That is, number of electrons contributed by ligand for the metal carbon atom. So as we have, if it donates one pair of electrons, and it is monodentate. If it donates two bidentate, and so on we have. So other than that, we have one, that is carbonyl. Carbonyl is treated here as a special ligand. Each terminal carbonyl contributes 2 electrons, and each bridging carbonyl contributes only 1 electron to the valency shell of metal atom. Third point, check the number of electrons donated to the valency shell of atom by conventional ligands present in the complex. That is, the other ligands which are attached to the central metal atom. Fourth point, check the number of electrons formally contributed to the valency shell of the metal by metal-metal bonds. So here each metal-metal bond contributes 1 electron to the valency shell of the metal in the complex. So along with the ligands, if there are bonds, metal-metal bonds, so then those also counted as 1 electron. So adding up of all these points, that is summation of number of electrons checked in steps 1, 2, 3 and 4, give the A, and that is effective atomic number or effective number of electrons in the valency shell of atom in its complex. So thank you. Next part we'll take in next class.